This is an introduction to Stpa. If you're new to Stpa, this is all about anticipating and preventing loss scenarios in complex systems. This video and the other short tutorials we're giving are not full training classes. I want to be very clear about that because there have been some misunderstandings in the past. This is just a short tutorial video. The objective of this presentation is not to make you an expert in the Stpa methodology. You can't do that in just an hour. It doesn't always take a whole lot of time to train folks in Stpa, but you can't do it in just an hour. Instead, the objective of this presentation is to introduce the core concepts and provide a general introduction to Stpa so that you can follow the Stpa presentations and results over the next few weeks. I think I'm going to start with a control structure. What is a control structure? Well, let's look at a block diagram first. This happens to be for a satellite system, but the application doesn't matter. The real insight from STAMP is a way to enable abstraction, is to focus on the stuff that matters when it comes to safety and accidents historically, to highlight that stuff and make it super obvious. And not emphasize the other details that historically have not been so relevant in accidents. So one way to do that is through control relationships. You can look at this block diagram and instead of starting with looking at components one at a time and saying, what if this guy fails, what if that guy fails? That's a bottom-up approach. What we would do in Stpa land is say, hey, look, this group of stuff here, that's the collection of stuff we have to move the satellite around in space. Let's call that a controlled process. That group of stuff working together is going to try to get us to move around in space. And let's look at what controls that process. Let's establish a control relationship. So this group of stuff, let's say, collectively, even if it doesn't look this way on silicon, collectively working together, this is a functional controller. That means it's something that's making decisions. It has a goal in mind that it's trying to achieve. It's providing actions to try to achieve that goal. It's monitoring for feedback oftentimes to see what's going on in the control process, what's the effect of our control actions. That feedback is used by every controller in the world to update something called a process model. Doesn't matter what's inside your controller. Could be a human, could be a piece of digital hardware, it could be software, it could be AI, but it's going to have a set of beliefs. We know this from control theory, and this is a very powerful idea. These beliefs are formed based on feedback. These are beliefs about the outside world, and they're central to how controllers make decisions. These beliefs are used to decide based on a control algorithm, what's the correct action to take in this situation. So if you think a tank is empty or you think a tank is full, you might take very different actions. And of course, those beliefs could be wrong. This captures a huge set of accidents. Now, this is not the only thing baked into STAMP and Stpa, but this is a central part that we're going to use over and over. So this is a slide you saw yesterday. We have some familiar language that we're going to use throughout this presentation. Control actions, feedback, process models, and control algorithms. This is the basics of control theory. Of course, in real systems, we don't just have one control loop. We have a hierarchy of control. Now, what you see on the right-hand side is called a control structure. So we're going to build these control structure models. You can see the vertical axis has meaning. To help us organize and keep track of things as human beings to try to manage complexity. The vertical axis indicates control. So the downward arrows are always going to be control actions and decisions that are being made, commands that are being sent. The upward arrows are always going to be feedback. Hey, this is what's going on. You figure out what to do with it. Often they're provided by sensors. And we've got a hierarchy of control on the vertical axis. This attitude controller in the spacecraft maybe is figuring out how to achieve some target orientation with those control actions towards the bottom here. But it's not smart enough to figure out where it should go. It just receives a target and figures out how to get there. Someone higher up has to send it the right target. That would be the navigation controller. We've got a different set of beliefs that are required for this controller to work, different kinds of feedback that it needs to receive for stable control, and so on. Now, we're going to build these 3-box control structures all day in these sessions. And a common sentiment that people have is, wait a minute, that's way too simplistic. Look at that block diagram on the left. That's what I'm used to doing. In fact, we've got 100 pages of that stuff. What are you doing hitting me with a 3-box control structure? That's way too simplistic. But remember the lesson you had yesterday about models and what models do. Anyone who's familiar with software engineering knows exactly what I'm talking about. Decades ago, we used to write code in assembly language, and this is the exact same algorithm in a more recent language called Java. The one on the left, I had to use 2 columns just to fit it on a slide. It's very difficult to read, very, very error prone. And a bit more complex to figure out what's going on and what could go wrong. On the right-hand side, this is much easier for a software engineer to read. Of course, it's much shorter. It's much closer to how humans think about systems and specify systems, but it's simpler. So how can this be? It's like a win-win. We've got a simpler way to do our job, and it's more powerful, and it's easier to understand. You don't get win-wins very often, but you do sometimes with abstraction. So complexity, I would respond to the sentiment at the top. Complexity is not the goal. Simple is a good thing as long as it works and achieves our objectives. All right, that was my quick review of yesterday. I'm not going to say anything more that you've already seen. I'm going to move on to methods. A common question we get is, what's the difference between STAMP and STPA and CAST and all of these acronyms? Yesterday was all about STAMP. STAMP says accidents are caused by inadequate control. It's got a taxonomy, it's got a language, it's got a way of thinking about accidents. There are some methods built on this model. This model does not have a step 1, a step 2, or a step 3. It's just a way of thinking about accidents beyond component failures, focusing on the interactions and the controls. We need methods if we're going to apply this to a system. So we've got some methods. One is called CAST. We'll hear more about this later this week. This is a method for applying it to an accident that happened in the past and figure out exactly what caused the accident and get a deep understanding of what went wrong. You'll see more about that later. Today is going to be about a different method called STPA. It's got the same foundation, the same kind of language, but STPA provides the methodology. There's a step 1, 2, 3, and 4. It says, okay, those are great ideas. How do I actually use them and apply it to my system? What do I do first, second, and so on? So the difference here is STAMP, and yesterday was mainly about the theory, and today is going to be about the methodology. How do we take those ideas and actually use them? All right. Let's move on to STPA. I'm going to take my own advice with abstraction. I'm going to start with a 30,000-foot view of STPA. You can't see any details at all from that high up, but you can see the bigger picture. Here's the bigger picture. What's it even for? It's a technique for development and for safety assessment. It can be used to anticipate hazardous scenarios. If you've got problems with these bulleted items in your system, STPA is probably a great tool for the job. This is what it was created for. Hazardous scenarios caused by software, computers, and automation, human error and confusion, system design errors, assumptions we never maybe recognized were assumptions and they were flawed, missing design requirements, interactions between systems. This is kind of the system's problem, and STPA is really, really strong for these kinds of problems. All right, I said it was a method. What are the steps? There are 4 major steps in STPA. Step 1 is to define the purpose of the analysis. Why are we applying STPA? What are we trying to prevent? Are we just trying to prevent a loss of life, or is it more than that? We'll talk more about losses in a moment, but that's the first step. What are we trying to prevent with STPA? Step 2 is we need a model. We're going to analyze a model. Well, we have to create the model, or if it doesn't exist, or at least draw and represent the model. That's step 2. Step 3 and 4 are about analyzing the model. You have to start somewhere. Where do you start? In STPA, we start with the downward arrows. These are the unsafe control actions, or the control actions that could be unsafe. We identify how they could be unsafe. We create some requirements there in step 3 to prevent them. But we're not done there, because we've only looked at the downward arrows. Now that we've identified what could go wrong, we've got to figure out why that might occur. Why in the world with these controllers that I spent so much effort designing, or I'm going to spend so much effort, why would they do these incredibly unsafe things? What in the world might they believe? So we're on step 4, constructing scenarios. What might they believe about the outside world that might not be true? What kind of feedback might lead them to have those beliefs inside the controllers? What kinds of process behaviors might cause some problems? And we build these scenarios to kind of poke holes in our concept or our design. We build scenarios to identify exactly what we've missed and what's wrong with our system. And of course, we have to build controls in place to deal with those. All right, that's the 30,000 foot view. I'm just going to go through this process 2 more times, but I'm going to do it in a little bit more detail each time. I've finished round number 1. Let's go in a little bit more detail. Let's look at a 10,000 foot view. So we're starting to see some streets, some contours here. Let's peel back the onion and look a little bit closer at these steps. All right, so step 1, I mentioned something about losses and what we're trying to prevent. These are super high level statements. Here's an example. In automotive, you might say we want to prevent a loss of life or injury. This is a stakeholder loss. Stakeholders could be passengers, they could be OEMs, they could be cities, municipalities, it could be all kinds of things. We want to identify what are the losses that stakeholders care about, and we can decide which ones are going to be within scope for our analysis. We don't have to stop with loss of life. We can say, what about damage to the vehicle? We don't kill anybody, but we destroy the vehicle. Do we care? Yeah, we probably care. And if we've got something in our design that's going to cause that, we'd like to know about it and fix it. Are there other losses? What about a loss of mission? There's generally always a loss of mission that you might want to consider. What's the mission in automotive? Well, transportation, getting from point A to point B. If we don't kill anybody, we don't destroy the car, but we don't bring passengers from point A to point B. Well, that's a problem, isn't it? I mean, maybe it's not as bad as killing people, but it's a problem, and we'd like to probably know about it if we're designing autonomous vehicles for ride sharing and things like that. We're not achieving our objective if we're causing L3, L4, loss of customer satisfaction. Really, any loss that is a high-level stakeholder loss is valid, and we can consider that and identify the causes of these losses in STPA. In fact, the rest of the analysis can be seen as a structured way to identify what are the causes of these losses and what do I have to do about them in my system. All right, so that's the 10,000 foot view of step 1. Let's look a little bit closer at the step 2. You've already seen a little bit of this. We already talked about control structures. Here's a quick example. We've got maybe operations management at the top, providing operating procedures to a human operator there. Those operators could be pilots or could be control room operators, depending on your application. We might have some automated controllers there in the middle. We might have some physical process at the bottom. We're going to build a control structure model of our system. I'll talk a lot more about this later, but here's a quick glimpse of what a snapshot of what one might look like at some point in time. And we're going to build these and analyze what can go wrong. We'll come back to control structures a little bit later. All right. Let's go on in our 10,000 foot view to step 3. Once we've got the control structure, we've got to look at those downward arrows and see what can go wrong. We call these unsafe control actions. So if we've got some command in our system, we ought to be looking at 4 ways that this can cause or lead to a hazard and a loss. If a command is not provided, that could be dangerous. What about a braking command in a car? You don't provide a braking command when there's an imminent collision. That sounds pretty bad. What about case 2? You do provide the braking command. Is there any case where that is dangerous? Sure, maybe you're on a highway, maybe you're in the middle of an intersection. There are situations where you don't want to provide the braking command. Aha, it sounds like situations might be just as important as the command. We'll get to that in a few moments. Case 3, what if we provide the command, but it's a little too early or too late? What about that braking command in a car? We provide the braking command in the right situation, but we're 3 seconds too late. That sounds like a safety problem. We better do something about that. What about case 4 here? We do provide the braking command. It's in the right situation. It's on time, but we immediately let go of the brake command after 3 seconds. We don't hold it down long enough, or we hold it down too long and come to a full stop on a highway. There are some ways that that could be dangerous as well, the timing aspects of the command. Now, there are sub cases we'll talk about after the intermission, particularly for the second column there. But these at a high level are all of the ways a control action can be unsafe. If you're thinking of a 5th way, where is that on the list? It's a subcase of one of these, and we'll talk more about those later. We'll also talk about how to identify a UCA, how to construct these things, and what the criteria are. But for now, I just want to show some examples of what these UCAs look like. So we went over the 4 categories of unsafe control actions that we use to guide this step of analysis. Once we identify how these control actions can be unsafe, we can immediately, we're not even done with the process, but we can immediately get some requirements. And the requirements look like this. Controller X shall provide command Y when D. Now that's interesting. Look at the components of that requirement. They're always going to be written just like this. And that satisfies a lot of the check marks we'd like to see on good requirements. So it says exactly what the output needs to be, command Y. It specifies exactly what situation it needs to be responding to. That's D. By the way, if it has to react to D, guess what? It better have some feedback or some indication that D is happening. That's another thing we're going to look for if we're going to enforce this requirement. And the responsibility is being assigned to controller X. Look at the next one in column 2. Controller X shall not provide command Y when E. Now, some of you just cringed a little bit. I understand. I lived that life for a long time. Shall nots in some industries are frowned upon for a good reason. They're very difficult or impossible to test. You can't prove them. You can't get paid by demonstrating that you've met those for sure, and contractual requirements and other problems like that. However, I don't think we should be ignoring those just because they're hard to demonstrate and to prove. Sometimes you can massage the language, but if you can't, the answer is not to erase these. Now, you can call them something else if that helps you get your job done. You can call them safety constraints instead of requirements, but these are really useful pieces of information if you're designing your system, and particularly from a safety perspective, if you're coming up with test cases and training cases and things like that. These are very, very useful. Anyway, if you like them or not, Stpa provides the whole spectrum here of requirements. You can decide what you need to do with them in your situation. The next one is the timing requirements within F seconds of G. And then we've got a different type of timing requirements, the duration requirements in the last column there. All right, so this is step 3. We identify the unsafe control actions. We get some nice requirements out of these immediately. By the way, there's a way to make these completely generated automatically and make these formally executable. We'll talk about that after the intermission. But let's move on to step 4. We've got the unsafe control actions, the ways that downward arrows could be unsafe. We're not done because we've got to look at other things in our system. Why in the world might my controller violate those requirements and do those unsafe things? It might think it's a good idea. Let's figure out why and make sure we've got the right controls in place to prevent it. So that's step 4. We identify loss scenarios. We start with an unsafe control action and we kind of work backward and we say, okay, how can the controller think this is a good idea? You get scenarios like this. Controller incorrectly believes X because the controller control algorithm does not enforce Y because maybe it received incorrect feedback Z. It was lied to, and that's why it thought it was a good idea. Because, and maybe there were sensor failures. So we do capture failures in Stpa only if they're relevant to the losses, by the way. But we do capture failures as well as non-failures. We've got a lot of scenarios where it was designed that way and we didn't realize it. There's one more type of scenario we've got to look at. What if the control action was not unsafe? It was the right thing to do, but it wasn't executed or it wasn't followed properly. There are a lot of reliability scenarios in here, but there are some interesting things as well beyond just reliability, component reliability issues. What if the command was sent, but it was not received? What if it was received, but it was ignored? Maybe it was ignored not just because something failed or lost power, but because we designed an arbitration algorithm that decided it was a low priority or something to that effect. It could be design-related causes as well. Of course, we've got failures in this category. All right, we're done. We've got the scenarios. There's only one last part. We can't just say we've identified how this is going to go wrong. I'm done. I'm going home. We've got to fix them. And that's the last part. Each of these scenarios provides a foundation to come up with recommendations and requirements. And they look like this. Component A should be able to respond within B seconds to avoid C. Component F shall automatically operate within G seconds when H. Notice the underlying part here. This is really important. How often do you come up with a requirement and 5 years later you scratch your head? Now, I know it was a good idea 5 years ago, but why did we write this again? The rationale and the intent behind this is documented because we have derived these from a specific loss scenario we're trying to prevent. So 5 years from now, if you want to change that requirement, okay, you know why we had it? We were trying to prevent scenario number 2. If you want to change that requirement, that's fine. You better have another way to prevent scenario scenario number 2 because that's where it came from. So this is the link between the problem space on the left, what can go wrong, which is where we're always operating in STPA land. A lot of reasons for that, confirmation bias and others. We always want to be challenging ourselves, not falling prey to thinking we've covered all of our bases. So we operate in the problem space on the left, and of course we map those into the solution space on the right. So these scenarios drive actions that we take. And we've got a whole spectrum of actions. We can make a new design decision. We can make a requirement. We can add a procedure for the human to try to deal with some of these. Maybe we should produce some operator training cases out of these scenarios so they don't see it for the first time when it actually happens and lives are on the line. We can produce test cases, factory acceptance tests. We can do recurring tests. We can do audits during operation to not only make sure it's not happening on day 1, but after 1 year, 5 years of operation, let's make sure we haven't drifted towards an unsafe state and these scenarios are starting to pop up. Don't wait for an accident to happen. We can identify these scenarios and the factors that are happening in the scenarios before something really goes wrong. All right, that's the process at a high level. I'm going to go through the last part once more for human interactions. It's exactly the same, but learning is a bit of a repetitive process, so I'll do it once more. We look at, for an operator, we start with unsafe control actions. Now, this is exactly the same as for automated controllers. Doesn't matter who's providing it. There are 4 ways a control action can be unsafe. Think about the braking command for a car. Now, when we get these unsafe control actions, we convert them, remember, into requirements. Well, we don't usually say that for operators. What we say is operator procedures, but look how they're written in STPA. Operator shall provide command X when D. We're satisfying all of those clarity and other nice criteria that we like to see on requirements for procedures. An interesting one there is the 3rd column, shall provide command X within Y seconds of F. A lot of systems have led to losses because we told operators what to do, but we didn't tell them they had Y seconds to do it. We almost handicapped them without that critical information. The last column is another one that's often overlooked as well. If you derive these with STPA, you can compare them to the procedures you already have to see what you've missed. If you're doing this earlier, which you should be, by the way, and you don't have procedures yet, this is how you develop your initial procedures in a very careful, systematic way. All right. Now that was unsafe control actions for humans. Let's go to step 4 for humans. You can see a lot of similarities. Once we have an unsafe control action, we've got to figure out why in the world a human would do that. What were they thinking, or what will they be thinking if this occurs? What kind of beliefs might they have? What kind of feedback might lie to them, and so on. And we build these scenarios. They look like this. The operator responded to a failure in A. That's why they did this thing. They were incorrectly believing X because, and X made it look much more reasonable to provide that control action. The operator does not perform Y because something else is happening. The operator received an incorrect feedback Z because something else. And we build these scenarios. We always explain why these are occurring, and that provides the foundation to make decisions and to put controls in place in our system, or to make changes. Or maybe we go back and remove some features and eliminate the problem altogether. The last case we've got to look for is, what if the operator provides a control action but it's not executed or not followed properly? So this would be a control action that gets sent. Maybe it's the right thing to do, but it doesn't work. It might be sent but not received. It might be received but it was ignored. Again, it could be due to some kind of failure, communications problem, or it could be because we've got multiple controllers here and we've got an arbitration scheme and we're ignoring some of our controllers because of the way we designed the system. So we build these scenarios, and again, we develop mitigations and controls to try to make sure we can handle these in our system. Design decisions and recommendations, requirements, procedures, and so on. All right, that's STPA at the 10,000 foot level. Traceability is maintained throughout. I'll show you that in a little bit. All of these artifacts from STPA are traceable all the way up to the losses that we started with. Remember, those losses were not all as important as each other. We might talk about rating severity of losses. That means every single result, all of the requirements, all the scenarios, all of the unsafe control actions are going to be prioritized based on the losses that they lead to. All right. Glimpse of a 1,000 foot view of this STPA process. Like the picture, this will show a little bit more detail than what we've done up to this point. We're not going to get much lower than a 1,000 foot view today. There is a lot more to STPA than we have time for right now, so you may want to look at the STPA handbook, or you may want to sign up for one of our longer classes or project-based workshops if you'd like to learn more about it. But today we're going to take a peek at the 1,000 foot view and see some of the additional structures and mechanisms that make this process work. So when we do step one, there's a little bit more than what I've told you about so far. We look at losses, that's true. Here's an example for a patient-controlled analgesia. So one loss here, by the way, this is if you're in a hospital, you're in pain, you don't have to wait for the nurse anymore. You can just hit this green button and it'll automatically dispense some pain medication. What are some losses here? Well, if you die, if the patients die, or if they're injured because of this, obviously that's a problem. What about a mission loss? Well, the mission of this thing is to relieve the patient's pain. Does that sound like a loss? Sure it is. If we're causing L2 with this system, then why are we even building it in the first place? Maybe it's not as important as L1, but we can identify the causes of these losses as well. Nuclear power plant. We've got loss of life or injury. What else do we have? What if we have some kind of damage? That's an economic loss. We've got to go fix it. These things are millions of dollars to replace if something goes wrong. We've got environmental contamination. That's another kind of a loss. What about the mission loss? Well, what's the mission here? It's to produce power and electricity. If we're not producing power, we're in trouble. By the way, these losses that we've been tossing around, I've been framing them in terms of safety, but have I actually been talking about security in disguise? How many of these are relevant to security? All of them are. This is exactly what an adversary would like to try to cause. So if we can identify the causes of these losses, would those be targets for an adversary? They sure would. We have a lot of overlap between safety and security here. Let's look at some military applications. What about loss of life or injury? Hey, that looks familiar. What about loss of mission? It might be a surveillance mission, an attack mission. What about loss of sensitive information, and so on? Again, safety and security are intertwined here, and they're going to stay intertwined for most of the process. We do have to refine losses a little bit in STPA. It's not enough. These are too high of a level to do much with. So we refine these into something called a system hazard. Now, here's the difference. An accident or a loss is any unacceptable loss. Could be injury, could be property damage, environmental pollution, and so on. But a system hazard narrows us down to the system that we're building or the system that we control. So the formal definition here is a system state or set of conditions that in a particular worst case environment will lead to a loss. Okay, so it doesn't mean it always leads to a loss, but it means that in a worst case, it will lead to a loss. Great example is the first row in this table here. In a chemical plant, a hazard might be the chemical plant releases toxic chemicals. How does that get us to a loss? Well, there might be a population nearby, and the wind might be blowing towards the population, and everybody gets hurt. That's no good. But what if the wind were blowing the other direction? Maybe we don't have that loss or don't have it quite to that degree. We are not going to try to control the wind. We're going to say that's outside of our system boundary. In this analysis, we want to zoom in on what's in our system boundary. What is the state of our system or the condition of our system that we would like to control and to prevent in order to prevent the loss. So that's one of the big differences between losses and hazards. The losses may involve lots of factors outside of our control, like the wind. The hazard zooms us in and focuses our attention on the thing that we can control, the system state that we're going to control and prevent in our design. Notice as I've been going through, these losses are not just what you might think of as traditional safety, depending on your industry. A loss is anything that is unacceptable. So from now on, anytime I use the word loss or unsafe or hazardous or anything like that, I am talking about any losses that we define. We get to define what they are. Okay, so let's talk about aviation. One loss, of course, is a loss of life. What are some other losses we might have in aviation? Fantastic. You can get a loss of the aircraft, of course. You can get a loss of the mission. What's the mission here? If we're talking about commercial aviation, the mission is transportation. We're not transporting people from A to B, right? So these are very, very high level stakeholder losses. Now, what about a system hazard? Well, we've got to figure out what the system is. What are we building? What is the thing that we control? Let's say it's the aircraft, okay, as a whole. So what can we say about states or conditions of the aircraft as a whole that we'd like to prevent? Well, here's I don't know if this video is going to come through for you, but here's a short little video of something we'd certainly like to prevent. This is to nudge you in the right direction. What's a system hazard that we would like to prevent in this system? New question. Certainly, if the aircraft are crashing into each other, that's no good. What if they're a millimeter away? Well, that's no good either, right? There is some distance, we call this minimum separation, where if they get closer than that, you're having a bad day. Things have really gone wrong. And we would like to maintain some minimum separation so that we prevent the losses. So one way to say the hazard here would be that the aircraft violate, or two aircraft violate some minimum separation. Okay, this is talking about a property or a state of the system, which is the aircraft as a whole here. Now, one way to specify these hazards is you've got to figure out what the system is, what the system boundary is. Let's say that's the aircraft. Specify what the condition is that's unsafe that you want to prevent. This would be violating minimum separation or getting too close to other aircraft. And you've got to link these back to the losses. Remember, every result is traceable all the way up to those losses. Here are some more examples for aircraft. Maybe we have a loss of aircraft control. Maybe the aircraft airframe integrity is degraded. We're not getting too close to other aircraft. We can control the thing just fine. We're not flying into the terrain, but something's wrong with the airframe integrity. We had a few years ago, we had a 5-foot gash torn into the fuselage of commercial aviation jets with passengers on board. That's not so good. What else can happen? There's nothing wrong with the airframe integrity, but what if the environment somehow is harmful to human health? We're kind of sitting in a tin can at 30,000 feet. The environment is not so great in a number of ways for human health. And even if we're not getting too close to other aircraft, there could be some problems here. This is about it. These 5 things capture just about everything we care about for aircraft in flight. There's a couple other for ground operations, but just about every accident you can think of that we've had in flight is a subcategory of one of these 5, is a cause of one of these 5 higher level conditions. All right, let's go to automotive. What about a loss of life, damage to the vehicle, loss of mission? Hey, these are looking pretty similar. And what about hazards? Now, let's say this system, we're an OEM and we're building the vehicle as a whole. What are some vehicle level states that we'd like to prevent? Well, we could say something about minimum distance. Again, we could say something about dangerous area or region. What about an operating envelope? Like there's no other cars around, so we don't have H1. We're not driving off a cliff or driving off the road, so we're not in H2. Is there any other way to cause a problem? What if we just slam on the brakes? You can actually injure people with emergency braking. What about if we pull some G's that flip the car over? That's not such a great day either. Even if you're staying on the road, you're not causing H2, and even if there's no other cars around, you're not causing H1. What else is left? Well, there's just about one other thing. What if the vehicle occupants are exposed to some harmful effects or health hazards? We have a fire on board. We have temperature that's excessive, and we've locked the windows and the doors, which maybe are electronic, and we don't have battery power, or whatever the cause may be. If we're causing H4, we don't even need to have one of the other hazards. We can still get to those losses. Okay, I'm going to skip a couple examples in the interest of time. Once we have these hazards, we translate those into system requirements. So if in automotive we said a vehicle does not maintain safe distance from nearby objects, and that's a system level hazard in Stpa, what's the system level requirement? Well, the vehicle must maintain safe distance from nearby objects. I didn't blow anybody's mind by writing down that requirement. This is not where you have the key discovery usually, but this is where you get the highest level level requirements. All of the other requirements we're going to derive from STPA are going to be linked up to these higher level requirements and hazards. So we're going to be creating a hierarchy, and this is just the top node of that hierarchy. Anybody who's done systems engineering and requirements engineering is very familiar with this concept of requirements hierarchy. In STPA land, we always derive the requirements from something that can go wrong on the left from the problem space. Let's move on to the control structure. A nice way to learn these beyond what I've already said is by showing you some examples. So here we've got a ballistic missile defense system, one of the first applications of STPA. We've got an early warning radar system here that sends a launch report, detects an incoming missile, sends a launch report to a fire control station. Fire control station selects a launch station somewhere in the world, sends a fire enable signal down to the launch station to go and deal with that incoming missile. The launch station then arms and launches the flight computer on a missile to go get it. The missile computer, when the time is right, sends the ignite command to the interceptor hardware. Every one of those is a downward arrow. It's a result of a decision. It's a control action, and it's informed in part by feedback that is bubbling up from the lower levels in the control structure. Here's another one. This is from a nuclear power plant. It's simplified, of course. This is an emergency flow control system, let's say. That's not the exact term, of course, but you get the idea. We've got some steam flow here that drives this pump and drives some water into our reactor to cool it. We've got a flow control system that sends some open commands to a valve to get the system started. One of the unsafe control actions is going to be if we do not open this valve when there's some kind of emergency, we are not providing emergency cooling, are we? We ought to look at why in the world this flow control system might think that's a good idea, what kinds of feedback can confuse it. Same exact thing we would look at for the operator and the control actions the operator provides. In a chemical plant, here's a little bit more of an organizational control structure. Let's say we don't have a lot of automation in this plant, but we've got some assistant operators in the field. We've got some control room operators here that are directly controlling some equipment. They're also monitoring and adjusting equipment through some field operators. We've got some maintenance workers that are replacing or repairing parts. They have to detect maintenance issues, which is one weakness we might want to think about. We've got a maintenance management control loop. We've got a plant management control loop here. We ought to be looking at the whole spectrum if we're really serious about safety, not just looking at the physical process, which a lot of approaches tend to do. All of this stuff is very important for safety. Whether you look at it or not is, I guess, your choice. But STPA is a great way to look at those interactions. Some of you are from the train and rail industry. Here we've got a centralized operator. We've got a train operator on the train, can provide some commands to accelerate or brake. We've got automatic train control system that can set speed commands to the train. There was an accident here. The accident involved this feedback being incorrect, reporting that the track ahead was vacant when really there was a train. Well, guess where this feedback goes? This feedback gets reported up to the central control room. So this wasn't really much of a backup because it was relying on similar information that the automatic train control system was. Guess what? The automatic train control system didn't stop. The central control room operator did not tell the train operator to stop, and the train operator was going around a corner and couldn't see the train, so that feedback wasn't working so well either. So this was a very quick snapshot of some of the causes in accidents. This is I don't think I'm going to go through this, but I wanted to give you a glimpse, some of the folks from Automotive, what this looks like for a more complex, slightly more complex automotive system. We've got a power steering controller here that can steer your car. This is a computer. It's controlled by another computer called a skid controller. A skid controller can take control of this guy and say, listen to me, ignore the driver because I declare we're in a skid, and drivers are notorious for doing the wrong thing in a skid. So this functionality is built into it. Does it sound like there could be some unsafe control actions there we better control for? There sure are. One thing you haven't seen yet is levels of iteration of a control structure. And that's important to see. A control structure is not something that's written in stone on day one and it stays fixed. It's really something that evolves and grows and iterates as you do development and as you do STPA. So here's a glimpse at that. Here's a level 1 control structure for an autonomous vehicle. The autonomous vehicle is way down here in this box. We're looking at these high-level control loops. Program management is going to have a go, no-go decision. What kind of feedback are they going to use to make that decision? There are some really important control loops here that never get analyzed, unfortunately. unfortunately. Let's call that a level 1 analysis. Let's zoom in at the bottom here. We'll call that a level 2 analysis. Once we do level 1, we'll come up with high-level requirements and constraints on this interaction, and we use that to drive decisions at level 2. Then we conduct a level 2 analysis and find out what can cause those higher level problems. And we look at the interaction between, maybe there's a pilot and a co-pilot, not my terms, by the way, but this would be the person in the driver's seat, person in the passenger seat of an autonomous vehicle during testing. We can then go to level 3. A lot of you folks are involved in autonomous vehicles. We can look at the brains of this operation here and look at things like control, planning, routing, prediction, perception, localization. This is a massive control loop. The stuff on the right is providing feedback up to the controllers on the left. Routing is a decision maker. It's receiving feedback from localization about where we are and making decisions about where to go from here and so on. Lots of unsafe control actions we have to control for, and scenarios that we are building into our system without realizing it. This is a dynamic positioning system used on ships and oil rigs and submarines and things like that. We have the physical ship is at the bottom here. We've got some thrusters and some other things that you can control. What controls the thrusters, let's say? Well, the thruster controller here controls RPM, pitch, and direction, but how does it know what RPM to achieve, what pitch, when to start, when to stop? Well, there's a dynamic positioning control system that provides those targets to the thruster controller. And each of these controllers has a process model over here, a set of beliefs about the outside world based on feedback and other information that it uses to make decisions. And this explains how some of these controllers can get confused. Of course, there's a lot more to STPA than just the process model, but that's one of the important concepts that is used later on. There's an operator, of course, at the top, a human being that sets some oversight over the dynamic positioning system, maybe can turn it on, can turn it off, things like that, receives feedback in the form of alerts and confirmation of certain modes are met. And we ought to be able to show in our analysis somewhere that we have considered each of these control loops and how they can go wrong, how the system can get confused, and show that we've got the right controls and requirements in place to ensure safe and secure operation. Notice the vertical axis, again, indicates control and authority. That means the downward arrows here are going to be the control actions, the instructions to achieve a safe state, and the upward arrows are feedback and information that we're using to monitor the system. This is a medical device used at PSI in Switzerland. This is a proton therapy machine. So a patient may lay down on this table here or a couch, and the patient's head might be here. And you might want to irradiate a tumor in their head, behind their eyeballs, but in front of their brain. So here's a proton beam that comes out of this. This is a gantry, and it irradiates the tumor. And we want to be very, very careful. You don't want to irradiate the brain tissue. You don't want to irradiate the eyes either. So this thing can move in all kinds of different ways. The table can move in all 3 dimensions, and we have, obviously it's a very safety critical system. Here's the facility. There's the cyclotron here to spin up a proton beam. It's a very large facility. We've got multiple beam paths here. After this thing gets spun up by the cyclotron, it comes out here and gets split amongst multiple different facilities. There's an experimental area. There are 2 gantries, and there's some other things. You could be doing research projects on this, not only irradiating patients, and some of these potentially could be operating at the same time. This is really interesting, but also incredibly safety critical. So we've got a lot of technology, right? We've got the cyclotron, we've got this beam path and control elements, things like sweeper magnets, degraders, collimators, phase slits, monitors, etc. It's an incredibly complex system to shoot proton beams into your skull with millimeter accuracy. So all of that buildup was for this question. How big do you think the control structure on the next slide is going to be? Take a minute and give me an answer. Some of you said 10 boxes. Let's say number of boxes. How many boxes do you think we've got? More than 10? Well, this is a bit of a trick question. I apologize. I set you up to do the wrong thing, but I did it on purpose so that I can be here when it happens. Some of you said 10, maybe less than 10, but some of you said maybe 100. One person said, maybe there's 1,000 boxes in the control structure. Well, the answer is 3. Now, this is a trick question. The answer isn't actually 3. It depends on how you do it. But I want to show you that the point of STPA is not to start at a detailed level. The point is to provide a top-down process, and that means starting at a high level of abstraction. All of that information I gave you, I was misleading you. And the fact of the matter is, you're going to be misled the next time you go to do STPA on a project, because you're probably going to be given all of this fancy technical information about your project. Sometimes you're given 1,000 pages of detailed technical design decisions and requirements and logic diagrams and schematics and P&IDs and things like that. That is not the starting point for STPA. The starting point for STPA is, look, all of that technology, all that fancy stuff I described to you, that lives inside a treatment delivery box, right? We don't start by looking at the detailed interactions inside the technology. What we do is we start by looking outside. Safety always depends on the context. Remember that lesson from the other day. So this is where we start in STPA. We say, what is the context of all this fancy equipment we want to build? Because if we don't understand the context, we're not going to have any idea whether we're building the right thing. We're not even going to know what to look for when we dive into the detail and look at all that technology. So what we do is we say, all right, look, what's the control action from this technology to whatever the process is? In this case, the control process might be the patient, and we're irradiating the patient. All right, we already knew that, big deal. What else do we have? Well, what about feedback? Do we need to be monitoring something about the patient? That's going to impact what technology we need. And we're not going to know what technology we need if we don't start here. You can give me 1,000 pages of a carefully designed piece of machine, and if it doesn't include the right feedback, you might not even notice without looking outside the technology, looking at the context of the environment. So what kind of information do we have to monitor for the patient? Well, turns out if you want millimeter accuracy inside somebody's head, guess what affects that? All kinds of things. Breathing is going to affect the position of the patient's head on the table, right? Of course, we can control the position of the table here, but if they're breathing in and out, then the treatment maybe takes several minutes to perform. Maybe it takes an hour to perform. Are we going to tell the patient to hold their breath for that long? No, right? So what are we going to do? Maybe we need to have some mechanism to monitor in real time the motion of the patient as they're breathing. Aha! Wow, well, that's going to impact the type of technology we have, right? We absolutely got to have these answers early, not find this out by chance after we perfectly built the wrong system. The other place we look in a control structure is above the stuff that we're building, right? What about the treatment definition? Before this technology can even be turned on, we need to have some physician up here that diagnoses the patient and determines the proper treatment and provides some treatment plan down to the treatment delivery system. Aha, what does that treatment plan look like? What are these doctors going to be providing? We better make sure our technology can handle the right types of treatment. Do we want to have a sweeping type of mechanism? What other kind of characteristics are going to be present in a treatment plan, right? And what kind of feedback do we need to provide back up to the treatment definition folks so that they can do their job properly? Maybe we need to have 2 visits. So the patient comes in first, has some imaging done. It might be the exact same equipment since we're already going to monitor the breathing in real time. And they come in and we monitor that and we provide some kind of imagery up to the treatment definition folks, some kind of confirmation of what they thought was happening, some additional information so that they can come up with a treatment plan, and then they provide the treatment plan back down, right? If we didn't have that insight, you can imagine going and perfectly building the wrong system with no way to enforce these constraints. You find out too late. You find out after the thing is already in the hospitals, and then what do? Well, then we're in a really tough situation. So that's where STPA starts. It starts at a super high level. 3 boxes is not a rule. It's not set in stone, but it happens to be a fantastic place to start in a lot of applications. So once you start with a very super high level, right? We call this treatment delivery box a black box, meaning it's like a black hole. You cannot see inside of that thing on day one, which is very good because we need to understand the context. But eventually we do need to look in more detail and understand what's going on inside that treatment delivery box. So take that red box and zoom in. So we zoom in. This will be a later iteration of the control structure. I told you the control structure evolves over time. Here's an example. Once we have a better idea of what the level 0 constraints are, let's say we zoom in a level and we say, all right, how is this? Here's the technology again. Still, we're not at the level of looking at valves and motors and encoders and things like that. We've got to figure out how this thing is operated in real time. There's going to be a set of operators that may need to be able to start treatment. There's going to be maybe a medical team standing by, monitoring maybe patient position. If the patient moves too much, or if there's some feedback that detects the patient has moved too much, maybe the medical team needs to be able to respond. Maybe there's a maintenance team in the loop somewhere providing hardware replacements. What kind of interaction do we need between the maintenance people and the operators? Should the operators know that maintenance was performed? Probably. What kinds of let's define these things and figure it out. Maybe the technology has some kind of knowledge that maintenance was set and the feedback is provided up here, right? We've got to figure all this stuff up. What are the commands that these entities are going to need to accomplish their job? What kind of feedback do we need to provide to them so they can do their job effectively, and figure that stuff out, do this level of analysis before we necessarily know what the automation needs to do to be safe, right? We've got to, this is what top-down means. We've got to start at this level of detail before we talk about sweeper magnets and phase coders and all that stuff that I gave you to point you in the wrong direction. So eventually we're going to do this analysis. We're going to come up with these constraints, and we're going to look at the ProScan facility, right? The actual technology is being used, all the actuators, the sensors, the automation, and so on. And this was done. All these slides, by the way, are real systems, and this is no exception. Unfortunately, the real system here is considered proprietary, so I can't show you any more information than this. But this shows you how you would iterate the control structure and iterate the STPA process as information becomes available, as decisions are made. This is really not just a linear process. It's an iterative process, like everything else in engineering. Let's do one together. All right. Adaptive cruise control. This is an automotive example. We've got radar in front bumpers these days. It shoots out in front of the car, detects cars in front, and what it will do is allow your car computer to maintain some set speed, and if a car gets too close, it will slow down for you. All right, let's give this a try. So I've started a control structure. Now in this system, we're going to be engaging braking and propulsion here. Let's take that as a starting point. And let's build out this control structure. So let's call that the physical layer at the bottom. What are some controllers that you would expect to see in this control structure? I've opened the new question. What's going to control braking and propulsion in this system? Driver is a big answer, of course, and you're right. By the way, how often do we see driver in an electrical schematic or an electrical block diagram? Not very often, because that's not what those diagrams are for, but they're critical for safety. And in STPA, we're not going to throw that problem over the fence. We're going to look at how it integrates and interacts with our system. So let's put driver there. What else do we have? Somebody mentioned cruise control. A lot of people mentioned cruise control. Let's put that down here. That would be some kind of computer maybe. All right. What kind of control actions would you expect to see from the computer? New question. So we've got maybe a downward arrow here from the computer. What kind of control actions do we need? Fantastic. So of course we've got maybe accelerate. We've got maybe braking. Let's start there. Now for cruise control, this is really adaptive cruise control. That's what they call these things. What kind of feedback do you think adaptive cruise control might need to monitor to make those decisions? New question. How's it going to know when to accelerate, when to brake? Fantastic. It's going to need to know speed. It's probably going to need to know distance. And we can start there. There's a lot more, of course, that it needs to know. Distance would be distance to car ahead, but it's okay to have an incomplete control structure. This doesn't have to be the finished, polished control structure. As you do the analysis, we will identify what's missing, what kinds of controls do we need for this thing to be safe and to be stable. Let's look at the driver. Now the driver's got all of the manual controls available to them. They can grab the wheel, step on the brake, step on the gas. They've got all of the regular feedback. They can look out the window. What other controls does the driver have? So the driver is going to have a downward arrow here. New question. What kind of control actions do you think we need to supervise this system? Fantastic. Right at the top of the list, it looks like we've got on off. Yeah, maybe they should turn it off. What else? Oh, maybe set speed. That was another popular one. What else? Maybe there's an override mechanism. Now the override could be through this command. It could be another way to route it through a manual command all the way on the left there. There might be a set distance command. If you've got one of these cars, you're familiar with how that works. All right, let's look at an upward arrow. Let's look at some feedback here. So what kind of feedback might the driver need to provide these commands? Let's look at the on-off command. Turning on, what kind of feedback do they need to know when it's a good idea to turn it on? And what about turning it off? What do they need to know? Fantastic. Well, they need to know, is it on or off, of course. What else do they need to know? They need to know if something's gone wrong, so there's probably some fault. If it's in a fault mode, probably you shouldn't be trying to turn it on. But what if there's some kind of malfunction that's not detected? I mean, if the thing is broken, maybe it's not able to detect its own fault very well. So what do we need for the driver to be able to know if adaptive cruise control is doing its job? What kind of variables might be hidden inside that ACC computer that would be really useful for the driver to know? Yeah, how about distance to the car in front? How about, have you detected the car in front? Now you might say as an engineer, but wait a minute, why am I gonna do that? You could just look out the window. That's better feedback, it's more intuitive and so on than looking at a dash and reading a number. But look, if we don't tell the driver what adaptive cruise control is thinking and seeing, what it thinks it sees, how are you going to know when it's time to turn off adaptive cruise control? Because imagine if we're driving along, adaptive cruise control doesn't see the car in front. When is the driver going to realize that? If we don't provide this feedback to the driver, when are they going to realize adaptive cruise control doesn't see the car in front? They're going to realize that when you're about to hit the car in front. That's going to be the first indication. It's going to be a visual indication here. Oh no, I've got 3 seconds to crash. It should have hit the brakes by now. What's going on? And then you take over control. We should provide some kind of anticipatory feedback here, so the driver's got a heads up before there's an imminent collision that, hey, adaptive cruise control is not even seeing this car in front at all. Maybe I should turn it off. Maybe it doesn't even know enough to figure out that it's in some kind of erroneous state. That would be really useful feedback, wouldn't it? Okay, so we haven't even done an analysis. We're just sketching out a control structure very crudely, and look at the insights that we're getting already. If you're familiar with early applications of this system, a lot of vehicles did not have that feedback, and it caused exactly the scenario that I just presented. Okay, so here's an example control structure. This is not finished, it's not complete, it's not intended to be, but this is a great starting point. When we do more control structures after the intermission, notice this pattern. We're going to see this a lot. Physical layer is generally at the bottom. We may have some automation layer in the middle. We may have humans at the top. This appears all the time in control structures. So if you're feeling lost, you don't know where to start, you might look back to a pattern like this and see if this is applicable to your system. Now, we're not done. We've got to do an analysis and figure out what can go wrong in the control structure. By the way, as I said, that's not the final one. That's just the first sketch. It might look like this by the time we're done with it. And we're not going to start with this amount of detail. We're going to start with something much simpler. We're going to start at a high level of abstraction, and we're going to use Stpa to make these decisions and make them right from the beginning. All right, let's go to step 3. Step 3 is to identify unsafe control actions. Here's an example. Driver does not provide the brake command when a forward collision is imminent. That sounds dangerous, doesn't it? Notice there are elements and ingredients that go into an unsafe control action. There's a source controller. Where is it coming from? There's a type. Are we talking about an action provided or not provided? What is the control action we're talking about? In this case, a brake command. And critically, what is the context that makes that control action unsafe? If I told you the driver this morning did not provide the brake command at 8:30 a.m., is that safe or not? We don't have the information we need to figure that out. I mean, maybe the car was sitting parked in a parking lot and it doesn't matter if you don't provide the brake command, or maybe you were approaching a red light. So the context is what makes the command safe or unsafe. Safety always depends on the context, and this is where we roll that into Stpa. In fact, when you do this in Stpa, those first 3 ingredients are going to be generated for you by the process. Your real job is to identify what's the context that makes this unsafe. Here's another example. Computer provides shift to park command while vehicle is moving. That doesn't sound so good. There are a couple other parts to an unsafe control action. We do need to provide that traceability at the end. UCAs trace back to the hazards, and the hazards trace back to the losses. We also should be giving these UCAs ID numbers or tag numbers so that we can link to them in the future steps. All right, why don't you try one? New question? Fill in the blank. Driver does not provide the park command before what? And these first 3 parts will be generated for you by Stpa. The first part comes from the control structure, and the next 2 parts come from a table. A lot of consistency and a lot of great ideas coming through. Of course, let me take a look here. Right at the top, we've got exiting the vehicle. And that's the answer that I've got on the next slide here. Of course, that's not the only one. There are others, but this is one of them. Now, what do we do with an unsafe control action once we write it down? Well, we create a requirement or a safety constraint. If this is unsafe, driver not providing shift to park before exiting is unsafe, guess what? The driver shall provide shift to park command before exiting the vehicle. If we're in an industry that creates procedures, that would be a great procedure. This is not so easy in automotive, so we might be thinking about what other ways do we have to enforce this constraint. Should we put a chime or some kind of feedback to remind them and say, hey, your door is open? That's something that really exists. Maybe we should give some other controller this responsibility, and maybe a certain number of people die every year because they forget to shift to park. What if we automatically shift it to park? There are some applications where that's been done as well. So we want to come up with ways to enforce, to prevent the UCAs or enforce the constraint. And if you want to move the responsibility to another component, that's possible too. All right, last step is to identify unsafe control actions. We build these scenarios, starting with the UCA. I like to use this diagram. There are some pitfalls here. It's very easy to use this as a checklist and to feel like you're done. That's not the intent here, and that's the danger of this diagram. But I do find it useful for people who've never done Stpa before to get you to your first scenario. So let's try that now. Let's say that UCA happens. A driver, let's say, does not provide a brake command when some obstacle is in front. What kind of belief do you think would lead to that driver not providing the brake command? What kind of belief? Driver believes what? You've got it. Fantastic answers. Driver believes there's no obstacle in front. One of the first places to look is the context part of the UCA. See where it says when obstacle is in front? If the driver doesn't know that that is the context, how in the world are they going to prevent that unsafe control action? That's going to be really tough for them. And we would proceed and build the rest of the scenario and say, now, why would they not think that there's an obstacle in front? Could the obstacle be obstructed? Could there be some other piece of automation that's sounding 50 different alarms in the car and distracting the driver or doing some other things? And we would build a scenario to explain what's going wrong, and then we'd put controls in place to handle that. The next step in the last type of scenario is what if the control action is not executed or not followed properly? Here's an example. Let's say the driver does provide the brake command, but the vehicle does not stop. So we'd be looking at the bottom left portion of the control loop, and we'd be looking at problems here. We'd say, what can go wrong with the actuator? Maybe some actuator can fail. Maybe somebody can lose power and the command doesn't get through. But what about a non-reliability problem? What about everything working exactly as designed? One of my favorites here is this controller down at the bottom. What if that controller decides to send a conflicting control action? We can think of a few on cars with lots of computers that can control brakes and throttle. For example, what about anti-lock brakes provides conflicting control actions to repetitively release the brakes, which is its function in a skid. It pulses the brakes. Guess what pulsing the brakes does if the driver is slamming on the brakes to stop as quickly as possible? Pulsing the brakes actually makes it harder to stop. Now, it's on all cars because it sacrifices stopping distance in favor of keeping directional control. So your steering wheel still steers your car because your front wheels don't lock up. But it intentionally, this is the design of the thing, will make your brake control action less effective. That's really interesting. As we get into autonomous vehicles, should the autonomous software at the top here maybe have the ability to override ABS if it knows, look, the priority is to stop. I don't really need steering control right now. I just need to stop. That's really interesting proposal, one that I don't think has been proposed, as far as I'm aware, on autonomous vehicles. ABS is just always enabled because that's in humans are not capable of making that decision in a panic situation, but maybe autonomy could, and it could make a better decision. Okay, so that's the 1,000-foot view of STPA. These scenarios are the accidents before they happen. They are about 3 or 4 bullet points. It's not a 100-page accident report, but this is the accident snippet, the flaw in your system demonstrated by a counter example, and you've got to go fix it. Don't wait for that to happen. Figure out what kinds of controls we can put in place to deal with this. And you can come up with requirements, design decisions, training cases. This is where engineers get to be engineers. We are fantastic problem solvers, but one of the problems historically has been we don't always solve the right problems, and we don't always know what problems need to be solved. We overlook problems on our systems sometimes until it's too late. So this is a directed way to identify what are the gaps and the vulnerabilities and the loss scenarios that we've got to handle, and we can identify some controls to deal with those. All right, there's lots more detail about STPA. I really wish that we could go for a few days on this, but that's not what we're going to do. We're just going to focus on the core concepts here. And I've given you some examples, lots of examples. What's left is a couple things. Look at the STPA handbook. That has a lot more detail about how to do STPA. The other thing you need is practice. It's not very common we find someone that just is able to read the book and instantly becomes an expert. It's something you've really got to learn by doing.